All right, so momentum is one of these physics concepts that is really tough to define what it is. It's not how fast something's going. It's not how much energy something has. It's kind of a weird sort of thing. The best definition I could come up with is that it is mass in motion, or the amount of motion something has. As far as the math part of it goes, P, lowercase p, not to be confused with power, which is capital P, lowercase p momentum is mass times velocity. So it's the product of those two things put together. The more momentum you have means either you have more mass or you have more velocity. To put it in other terms, a semi-truck going down the road has a lot of momentum because it's moving fast and it has a lot of mass. On the other hand, a softball, baseball being thrown at the same speed that the truck is moving has a lot less momentum because its mass is much smaller. So basically, when we're talking about momentum, it's mass and velocity are the two things that matter. Momentum is a vector, which means the direction of the velocity matters as well. And we'll get into questions like that, where we're going to define positive, negative, sort of things like that. And again, just like any other vector question, what you define as positive or negative is completely your choice. You just get to make that call. Okay, next part is changes in momentum. So we know that we can change the momentum of an object. We can make it speed up or slow down. We can add mass or remove mass to it. Those are the only two ways we can cause the momentum to change, changing the mass or changing the velocity. Now, impulse, as we're going to talk about it, most of the time we are talking about changing the velocity. Very, very rarely are we adding mass to something or taking mass away from something to change its momentum. In light of that, we end up with this delta P equals F delta T equation. This is the impulse equation that is on your reference tables. And it comes right out of Newton's second law. If we have forces on an object, we can get an acceleration. Well, acceleration is just the change in velocity over time, a little bit of rearranging, and we get this delta P equals F delta T. So anytime we are changing the mass or changing the velocity, we have an impulse going on there. And the other way we can find impulse, besides doing and knowing masses and velocities, is to look at the area of this force time graph. Okay, so just like we did way back when with velocity time graphs and the area was distance, or work distance, force distance graphs and the area is work, we can do the final part, which is doing the force time graph, and the area is the impulse, the change in momentum. Okay, moving on then. Next part, conservation of momentum. Whoa, clicking way too fast. There we go. Conservation of momentum. If we don't have a force acting on our objects, if our F is 0, not existing there, that means that we don't have a change in momentum. In this case, we have conservation of momentum. The momentum before and after whatever we're talking about doesn't change. This is a law of physics. In fact, it's probably the second law of physics that you guys learned. Right after conservation of energy, we have conservation of momentum. And then these are 2 out of the 3 conservation laws you guys need to know for the newly revised AP exam. The third being conservation of angular momentum, which we'll get to when we do a recap of rotational motion. So basically, if you have internal forces, if you define your system of objects and any force that happens inside there, and all the forces happen inside there, then you have conservation of momentum. P before equals P after. There's no change in the mass times velocity of the entire system. This law actually comes out of Newton's third law, because when 2 things collide, they will give equal and opposite forces for the same amount of time, which means they have equal and opposite momentums. impulses. So whenever one gains, the other one loses, and the total stays the same. So when I'm talking with my kids about this, really we talk about momentum being transferred from one object to another. That's what conservation of momentum means. We're giving momentum from one object to another one. All right, and now in this, there are three main types of collisions. And this graphic did not come out to be super clear, so I apologize for that. But we have what's known as inelastic collisions, perfectly inelastic collisions, and elastic collisions. Now, out of those, which ones do you absolutely need to remember is the elastic kind. An elastic collision is special because not only is momentum the same before and after, but also the kinetic energy is the same before and after. We don't gain or lose momentum, but we also don't gain or lose kinetic energy. Now, this happens anytime, or this can happen anytime that two objects are going to bounce off each other, or one bounces off the other, and they are moving separate from each other. Anytime we get two objects hitting and sticking together, like, for example, an arrow gets shot into an apple, or a bullet gets stuck into a block, or two cars smash together and move together as one object. Those times are inelastic collisions, and kinetic energy is not the same before and after. We lose some energy because they deform, or some of the energy goes into sound or friction or heat or something like that. All right. So elastic collisions, the middle one on this choice here, we are talking about keeping the energy and the momentum the same before and after. The other ones, we're talking about getting the momentum the same before and after, but the energy will change. Let's talk about how you would go about solving one of these momentum problems. And I'm doing it specifically for conservation of momentum, but you could really do it in any momentum situation. And basically, when I teach this, I tell my kids it's 4 steps. Step 1, does P before equals P after apply here? Are we dealing with a situation that has no friction or no forces that are outside of my 2 objects or 3 objects or whatever I care about? If that's good, we get to move on. If not, we have to go to maybe delta P equals F delta T or some other way of getting to the answer here. Okay. Then we write out P before equals P after. We expand our definition to include all the objects before and after the event, watching out for directions because vectors are important. And then we kind of just solve for the unknown, solve for whatever we're looking for in this question. All right. And with that being said, now it's your chance to practice some momentum questions. There we go. Okay, so this is a sample FRQ. By no means am I going to say this exact style of question is going to show up on the exam, but this is something you could be asked to do with momentum as an FRQ on the exam. Okay, so we're told we have a car moving at 2 meters per second, colliding into the back of a truck. So truck stopped at a stop sign or something, the car comes, runs right into it. And it is claimed by somebody saying that if this happens, an elastic collision is more dangerous for the passengers than an inelastic collision. And we're given a couple examples here. For the elastic one, we're going to assume the car bounces off with a speed of 0.4 meters per second in the opposite direction, and the truck goes forward. For the inelastic one, they hit and stick and move together. Okay, so to prove this, or support or refute this claim, depending on what we're trying to do here, we're going to go through and try to figure out what is the final speed of the truck after the collision, when it's elastic, when it's inelastic, and then is this claim that an elastic collision is more dangerous valid or not? How do we go about dealing with that? All right, so let me switch over to the camera and then we'll get set on solving this. Let's see. Does this work? Yes. And bigger. Okay, there we go. All right. So the same question you guys just had on here. All right. So where do we start? Well, we've got two different kinds of collisions going on here. We've got the car and truck moving beforehand, and this is the same for both collisions. So this is our before. And then after, either they bounce off or they stick together. And we're supposed to find the final speed of the truck after each of these things. All right, let's see if I can, well, that actually got really blurry. So let's look at part A to begin with here. So beforehand, how many objects do I have that I care about? In this case, I have two of them. I've got the car and I've got the truck. And that means I can branch out this P before statement to say I'm really talking about the momentum of the car plus the momentum of the truck beforehand. And then afterwards, I must get the momentum of, again, the car and the truck as two separate things. So this is P car after plus P truck after. Now, you can come up with your own symbology and stuff like that. I'm just going to stick with this one. Can I zoom in? Yeah, I can zoom in. Okay. That might be a little better just so you can see this a bit clearer. There, and then one more zoom. Okay. So hopefully that's a little bit clearer to read here. Okay, so now branching this out one more time that I've got my two things going on here, before and after. The car, beforehand, 2 meters per second, and has a mass of 1.2 times 10 to the third kilograms. So M car, V car. I'm going to keep it in symbols for right now. I will get to the plugging in numbers later on, but I always recommend doing this with symbols first, then numbers at the end, just to make it a little bit clearer for what's going on here. All right. So we've got these things going on before and after. Now, let's look at the truck. Well, the truck has no velocity. It's stationary. It's sitting right there, which means it doesn't need to have any momentum because its velocity is 0. M times 0 is still 0, so I'm just going to leave it as a 0 there. Afterwards, we have the mass of the car times the velocity of the car after the collision, which we were told is a negative 0.4 meters per second, plus the mass of the truck times the velocity of the truck. And it's that velocity of the truck is what we're looking for. All right. So let's go through a little bit of algebra. MC VC minus MC VCA all divided by MT equals VT. Okay, so subtract this term over, divide by the mass, and we're left with our expression. Now here's the point where I would go and actually plug in numbers. And we will end up with a velocity for the truck, let's see, of 1.6 meters per second. Okay. So we take all those numbers, we take the mass of the car, velocity beforehand, velocity afterwards, with that negative sign because we're doing two different directions, and the mass of the truck up there, and then smash it all together, we end up with that 1.6 meters per second as our velocity. And that's part A. So in this case, the truck gets a nice bump and starts moving decently fast. All right, part B, we have to do the same thing for the truck, but now we have an inelastic collision. We've got a collision where they're going to stick together. Well, we start off the same way. P before equals P after on here. And we've got, again, two objects beforehand, momentum of the car plus 0. I'm going to skip the writing out the truck part because we both know that it's going to stop and it's not moving beforehand. The difference part here is afterwards, the two things are stuck together. So instead of having two separate terms for the momentum, I only have one. I just have momentum in the car and the truck stuck together as one unit. So two objects beforehand, but only one object afterwards. So this becomes MCVC. Again, 0 doesn't matter. And now afterwards, because they stick together, because they are now one unit stuck together, their momentums are the same. And we can write this as the mass of the car plus the mass of the truck times the velocity, I guess, of the truck. It's 1v there. It's one term. Okay. And this means that MCVC divided by MC plus MT equals VT. All right. Now, without looking too in depth at the difference between part A and part B, this number, whatever this works out to be, has got to be smaller than this side. We don't have any subtraction in the numerator. We're dividing by a much bigger number. We're looking at a smaller number overall here, simply because our denominator is so much bigger. And in fact, if you do the math out, we get this to be equal to, what do we get this to be equal to? We get this to be equal to 0.8, 0.8 meters per second. So we can argue pretty convincingly, I think, part B's collision, the inelastic collision, is definitely safer for the people in the truck. The truck is going slower in part B than it was in part A. But what about the people in the car? Are the people in the car better off in B, or are they better off in A? And that one bears some thinking about. All right, so for that, I'm going to switch back to the slides because I wrote this one out. All right, so there's the math. All these answers are in the slides. So if you want to come back through, check out these slides later on. All the work is in there too. So, but what I want to get into is this one, where we're solving part C. Okay, and solving part C, basically, we can use part A and part B to say, yeah, it's safer for the truck. But my justification here is all focused on the car. The car also has about twice the change in momentum going on here. And in fact, I realized I missed a negative sign. That should be negative 1440 in there. So the car's momentum is twice as much, or change in momentum is twice as much in the elastic, because we go in and we bounce off. We have enough momentum to come down to a stop, then have enough momentum to go back in that negative direction. Big, big, big change in momentum. To put it in perspective, if that collision took a second, that's about 3,000 newtons worth of force on somebody in that car. It's kind of crazy. This one, with the inelastic collision crashing between them, we end up with half the force. So even if we have to collide, we're going to have a safer experience if the two vehicles crumple and stick together. That is why on modern cars, they are designed to crumple and break and bend and flex to make sure that you are not getting you're not getting an elastic collision. You're getting an inelastic collision for every single one of those cases to keep you safe. Okay. So this is the gist behind it. Elastic collisions, you actually have a bigger change in momentum, moving, stopped, and then going in that negative direction than you do just moving forward. All right, questions on this question? Please throw something up in the chat so I know we are ready to move on. And if not, throw up a question so we can address it. Good. Okay. So there's one good. I'm going to treat that as we're good to move on. All right. Cool. All right. Then, so a lot of the questions with momentum are going to be along the veins of that one we just did. Crashing together, figure out how fast something's going, or head on, bounces off, sort of stuff like that. The other big type of question that you could be asked to do is one that involves a graph. And since the AP is really shifting towards free response questions, I'm going to guess we'll see a lot more of this type of graph question on there. It's just my opinion. It's not confirmed or anything. But I can ask you a lot more questions involving a graph that really test your knowledge than I can from a simple plug and chug mathematical sort of equation. All right. So in this case, we've got a cart moving at a constant speed of 3 meters per second. It's going to smack into the back of another cart, and then stuff is going to happen. All right. We don't know the mass of the second cart, but we do know the force. This may actually be a lab that you could actually recreate or be asked to do. This is one that I typically try to do with my AP kids, where you put a force sensor on one cart and smack it into things and look at the graph and try to figure out the change in momentum of that cart. So you're going to force versus time graph. Notice the units. That's the big thing here. Whenever you get a graph question, these units are kind of weird. These are in kilonewtons and milliseconds. So thousands of newtons and 0.001 seconds, or thousandths of a second going on there. Not your typical units, but it's going to work out, and there's a reason they chose those units for it. Okay, we get to ignore friction at any point here, and we're supposed to figure out two parts: the magnitude and direction of the 2 kilogram cart after the collision, and the mass of the second cart. So how fast is that first cart going after the collision? And then finally, how big is that second cart? All right, so let's dive into this one. Let me switch over. I don't think I put up answers to this one on here. I did not. Okay. This was one I didn't have time to throw up. So we'll just work through this, and I will work on doing a video, or at least a doc of these answers, and throw them in there too. Let's go back to the camera here where we can take a look at, there it is. Close, big screen. Okay, so there's the camera up there. Let's take a look at trying to solve this one. All right, so we are given a force versus time graph. And we are told we are supposed to find the magnitude and direction of the impulse of the second cart. All right, well, we're given a force time graph, which means we've got to do something with forces and times. There's not really much of another option going on here. So because we've got forces and times, let's work with forces and times. That to me says we're doing momentum. We're doing impulse. We're looking at the area under this graph. And if we don't have an area, we don't have much to work with here. So just like every other question we're going to be doing that involves area here, you're going to be given some sort of nice, easy geometric shape. Okay, so in this case, we're given a triangle. So I know the area of a triangle must be equal to the impulse, which is equal to the change in momentum. Okay, and the area of this triangle is 1/2 base times height, must equal delta P. So 1/2, my base is 1 full second. So, so 1 millisecond. Let me get my units in there. And the height is 10 kilonewtons. So 10 kilonewtons. And that must be my delta P. All right, so we go through. Now, let's see. So 1/1000th, this is 1/2 of 0.001 seconds, times 10,000 newtons equals delta P. This cancels out with that very nicely, and we're left with 1/2 of 10, or 5 Newton seconds is my change in momentum. All right, and that's wonderful. We are almost done, because now I know how much my momentum changed by, and the question told me how much momentum I started with. Okay, wonderful. So we can say that delta P must be equal to my final momentum, P final, minus my initial momentum, P initial. Oh, hold on a second. Something doesn't make sense. You guys see what it is? Take a minute and think through this. It's a problem with my number, but it's not a problem with the math. It's a conceptual thing, not a actual mathematical mistake I made. All right, so here's a hint. If this cart runs into this, should this cart end up going faster or slower after the collision? All right, so this one should actually be going slower, right? We wouldn't expect this cart, this first cart, to suddenly get a boost and go faster when it's already running into something else, which means my change in momentum has to be negative. It's got to slow it down and be a negative change instead of a positive change. So this cart will have a negative change in momentum, and this cart is going to have the positive change in momentum on there. So this is the one big tricky part to this question, is throwing that negative sign in there, because we know we have to slow down and move in the negative direction after we collide. So this will be 2 kilograms times V minus 2 kilograms times 3 meters per second. All right. Yep, so 6, 5, add it over, that gives us 1. 1 equals 2V. V must be 1/2 meter per second. Let's write it as 0.5 meters per second. All right, so there's our magnitude, 0.5 meters per second. And the direction, well, this is still a positive number, which means we are going to the right. Okay, if that was a negative number, we'd be going to the left, because it's the opposite direction in there. All right. And the last part, calculating the mass of the second cart. So here we've got to figure out the mass of the second cart. We can do this 2 different ways. It actually doesn't really matter. Yeah, but let's do conservation of momentum. That way it's going to make the most sense here. So this is a collision. So I get to use P before equals P after. Those 2 parts still get to apply because we still have a collision going on. Beforehand, I have 2 objects that I care about. So I've got 3 times 2 plus 0. So the moving cart and the stationary cart, the one that's not moving, must be equal to, what do we say? We said 2 times 0.5. So this is the momentum of the other cart after the collision, which we've got the velocity. The mass didn't change. You can't see the mass. The mass didn't change. So that's still going on there. And then we have to add in the mass m times its speed. Okay, and they tell us here it acquires a speed of 1.6 meters per second to the right. So m times 1.6 meters per second. And now we just get to do a little algebra here. 6 equals 1 plus 1.6 m. We do a little division, and we end up with m being 3.125 kilograms. All right, so that one is one way to do this question. The other way to do this question is to say that, well, the other cart, the moving cart, must have the same equal and opposite change in momentum. Because if P before equals P after, this is a collision where we're not going to lose any momentum. Whatever this one goes down by, the other cart must go up by that same amount. So we could also have done, or we could do delta P equals P final minus 0 because the cart wasn't moving at the beginning. So this is 5 Newton seconds equals m times 1.6 meters per second, and we still get the 3.125 kilograms for that. This one, this impulse is positive because we know it has to be equal and opposite to the negative one that the other cart had. So either way you want to do it, you get the same answer 2 different ways for that question. But the big idea here, we're using the graph. The area of that graph is the moment or the change in momentum, and then use either the delta P is F delta T or P before equals P after, depending on what they're asking you to do to solve those questions. And then finally, let's go on to the last question that I've got, and then we can move on to your Q&A about anything else that you want to cover. All right, let's see, can I get this whole thing in here? Pretty good. Okay, so for this one, we're told several students are riding in bumper cars at an amusement park. The combined mass of cart A and its occupants is 250 kilograms. Cart B has 2 kilograms. Car A is 15 meters away from car B and moving to the right at 2 meters per second when the driver decides to bump into car B, which is at rest. All right, so part A. Car A accelerates at 1.5 meters per second squared to a speed of 5 meters per second and continues at a constant velocity until it strikes car B. Calculate the total time for car A to travel the 15 meters. All right, how do we want to do this? There's actually quite a few different ways you could do it. All right, think about it. I know this topic, this part of this question, goes way back to the beginning of the year. So I understand if this is something we have to dredge out of our brains because, yeah, this is a typical AP question. We're going to be pulling from multiple units at the same time in here. So we're given an acceleration. We're given an initial speed and a final speed. And then we have to go a distance in here. So all this stuff put together says we're looking at some sort of kinematics equations. And there are a few kinematics equations that could help us here. V equals V naught plus AT could be useful. We might want to do V squared equals V naught squared plus 2A delta X, or X equals X naught plus V naught T plus 1/2 AT squared. Those three, right off your reference tables, they're the ones we got to use. So it really comes down to which ones that you feel like using. And again, the way I'm going to do it is not the only way to do it. This is just the one that I'm thinking of right now looking at this question. All right. So because this part is asking us for a time, I'm really not going to want to use the one that doesn't have time in it. Okay, that's one that I'm not going to use simply because it's not going to help me a ton right now. But I do like this one, and I do like this last one. The first equation will be useful to figure out how long it takes to get up to that speed, because I know what A is, and I know what V and V naught are, so I can find T there. And the other equation I can use to figure out once I get to that speed, how long does it take for me to actually get that 15 meters? So if I'm looking at part A here, I'm going to start with V equals V naught plus AT. T is going to be, subtract, divide, V minus V naught over A. So this is 5 meters per second minus 2 meters per second over 1.5 meters per second squared. So that's 3 divided by 1.5. That takes a total of 2 seconds. So this is 2 seconds to accelerate to 5 meters per second. After that, I know I'm at 5 meters per second now. Now I need to go the rest of the distance. Okay. So actually, we need to figure out how long it took me to actually get up there. So maybe I'm going to use this one. Let's pull this one down here, because now that I look at it, this could be a useful thing to know too. V squared equals V naught squared plus 2a delta x. So 5 squared minus 2 squared over 2 times 1.5 equals delta x. So 25 minus 4, that's 21. 21 divided by 3 is 7. So I went 7 meters in 2 seconds while we were accelerating. Now we need to go the rest of the distance. So now we need to go 8 more meters at 5 meters per second. So now we'll bring in the other part here, which is the x equals x naught. So in this case, I have to go 8 meters. I don't have any special x naught things. I'm going 5 meters per second. I'm looking for t. And we've reached our top speed, which means we're not accelerating anymore. We're going to keep going at our constant velocity, because that's what the question says. We accelerate and then go at a constant velocity. So 8/5. Let's think here. So that looks like 1.6. So this is the constant velocity to travel our 8 meters, which means our total time must be equal to our accelerating plus our constant velocity part. So our total time, 3.6 seconds. All right. So there's the kinematics chunk of that, and that's the kind of review. Way back when, I will preface this by saying, most of the time, we don't use kinematics equations on a free response question. Unless it's projectile motion, very rarely do we actually have to pull out these equations again. Normally, we can do it with energy or forces or something like that. But just keep it in your back pocket. These do show up from time to time, and they're kind of necessary. So when you're reviewing for the exam, don't skimp the very first unit and think, oh, well, we don't use those very much anymore. You're right. But when you do, you need to use them. Okay, let's move on to part B, because that was the standalone part, part A. Get the time, and now we're good here. So part B, after the collision, car B moves to the right at a speed of 4.8 meters per second. Calculate the speed of car A, and then we got to do the direction, and we got to do elastic. Okay. So speed of car A after the collision, I know mass, I know velocity, I know other mass, and I know other velocity. So this looks like it's a P before equals P after sort of deal. That just looks like I got a whole lot more murky in here. That's better with my hand, but not better with the other stuff. All right, let me know if you guys can read this. If this isn't good, I'll switch over to something else. But this is a P before equals P after sort of problem for part I. So beforehand, we've got two objects. I've got car A and car B. So the momentum of car A plus the momentum of car B. Beforehand must equal the same things afterwards. We're not combining anything together. There's no indication in here that we are stuck together or anything like that. So it looks like we just have to treat it as 4 objects here. So car A, mass of car A is 250 kilograms, moving at 5 meters per second, because that's the speed they told us here. Car B is at rest, right? So not moving, no momentum. Afterwards, we've got to figure out the velocity of car A, so that's 250 kilograms times V plus 200 kilograms. There's the mass of car B times the speed of car B, which they tell us is 4.8 meters per second. All right, here's where we'll grab a calculator and do some number crunching. So if we do this, 250 times 5, 1250 equals 250V plus 800. You know, we're going to consult Google on this. This is where you've got a calculator, you're going to use it. I don't have a calculator on me because I wasn't prepared. It's bad me. This is 960. So 1250 minus 960 is 290 divided by 250 is 1.2 meters per second. Okay, 1.2 meters per second. And the second part of this question tells us the direction. Are we going left, right, or are we stopped? Well, obviously we're not stopped. We have a velocity. So this one is not allowed in here. And it's a positive velocity. Because we said that this 2 meters per second going to the right was a positive number, that means that this number is also going to the right. On here. All right. If this number was negative, we'd be going to the left. But we don't have that case, so we're going to the right in this case. All right. And the final part to this question, is this elastic? Okay, going back to our definitions at the beginning of the stream, elastic means the kinetic energy beforehand is equal to the kinetic energy afterwards. So let's try to calculate some stuff out here. So the kinetic energy before the collision, well, the only thing moving was car A. So I have to do 1/2 mass of A V of A squared. So that's 1/2 of 250 kilograms times 5 meters per second squared. And that comes out to be 3,125 joules of kinetic energy. Kinetic energy afterwards, well, afterwards, I now have 2 different objects. All right, I've got car A moving at 1.2 meters per second and car B moving at 4.8 meters per second. So I have to do the kinetic energy for both of those and then add them together. So 1/2 MAVA squared plus 1/2 MBVB squared. 2 separate objects. So 1/2 of 250 times 1.2 plus 1/2 of 200 times 4.8 squared. And when you crunch all these numbers, we get a wonderful energy of 2,484 joules. All right. So, with that in mind, is this an elastic collision? Our answer is no, it is not. And our justification for this, kinetic energy before and after the collision is not the same. And there's my justification right there. And if they ask for a paragraph, we'll throw the numbers in and stuff like that. But yeah, there we go.